no questions. Are there any lingering questions for homework 1? No questions? All right, then. Let's move on to homework number 2. I think we made a little bit of headway into homework 2 in our last exciting digital design class. But maybe you guys have some questions that you'd like me to try and cover. Any specific questions that you'd like me to do in homework 2?
I have a couple, Professor.
All righty. What do you got?
9, 19, and 20.
All right, so let's try and write that down. 9, 19, 19, and 20. Any others that somebody would like me to cover? All right, well, let's do that. I'm going to skip ahead then, and we'll go to 9. And it's, here's the first one, and this is sort of an interesting idea. If you have an inverter, the input is A, and the output is A prime. That's all right. If you have a NAND gate, well, let's just start with an AND gate. If you have an AND gate, the input is A and B, and the output is AB. But what happens if you add an inverter to the NAND gate? Well, then what you get is AB, and then the output, which is AB inverted. And that's equal to not A or not B by De Morgan's theorem. So then you think, well, you know, I can do the same thing, only instead of calling it an AND gate, I'll call it a NAND gate, right? So we take the inverter and we concatenate it with the AND gate by showing a little dot. So that dot makes the difference. And now we have A prime or B prime by virtue of De Morgan's theorem. But suppose you take the AND gate, or the NAND gate in this case, and you wire it together. Wire the inputs together so A equals B. And so the only input is A.
Yeah.
Then the output is going to be A prime. I think somebody's got their mic open. Unless you got a question. So then what you want to do here is say that this is equivalent to an inverter with A going in and A prime coming out. So in other words, a NAND gate with its inputs wired together is the same exact thing as an inverter in terms of the Boolean algebra. And now comes an interesting question. What happens if you take an inverter, wire it to another inverter, and then wire it to another inverter, and then take the output and wire it back onto the input? What'll you get? Well, if this is a 0, that'll be a 1. Then this will be a 0, and then that'll be a 1. And the 1 will propagate through and change this 0 to a 1, which will change this to a 0, change this to a 1, change this to a 0, and then propagate through, and then change the 1 to a 0 again. And then this will get changed to a 1, that'll get changed to a 0, and this will get changed to 1. You built a buzzer. In fact, what you have here is a clock, which can be written in summary as a square wave in a box. And so that is a ring oscillator. So that's a very interesting idea. And so if you have 3 NAND gates, it's the same thing. It's equivalent to 3 inverters, and that is also a ring oscillator. So you can use either And in fact, if you go to the stockroom, you'll find the 7400, which is a TTL or transistor logic dual inline package, also known as a DIP. And it has 4 NAND gates built in. So you basically can get a ring oscillator for free just by going to the 7400 and wiring it up, give it some power, and blammo, you'll have a square wave for a clock. What do you think of that?
Professor, I have a question.
Sure.
You said it has 4 NAND gates, but wouldn't the output of it just be like 1 or 0, whichever you started with?
Well, yeah, in the case of 1 NAND gate, that's true. But in the case of 3 NAND gates that are fed back to one another, as shown in the illustration, it's not correct, because what happens is the output is unstable. It changes from a 0 to a 1. And when that happens, the input changes from a 0 to a 1, in which case the output changes from a 1 back to a 0. And so it keeps chasing its tail. So
Okay,
this is not stable. Right? And you can see that, right? Because here, let's try it again. Only this time, I'm going to keep 19 and 20 handy here because I haven't done those yet. But what we'll do is we'll run an experiment. If A is on input, then the output must be A prime. If A prime is on input, then the output must be A. If A is on input, then the output must be A prime. But if A prime is on output and you wire the output to the input, then didn't you just change A from A to A prime? And if you've changed that to A prime, then this is no longer A prime, it's A. Then this becomes A prime, which means this becomes A. And now if that's A, wait a minute, this can't be A prime anymore, this has to be A. In other words, when you do the analysis and let it flow through the gates, you'll see it keeps changing from A to A prime, which means the 1 keeps changing from a 1 to a 0. Now that's different than if you did something like this. Now if I have A, this is A prime, and this is A, and now you have a way to store a bit. And this is 1 bit of static memory. So in effect, you can make a storage element with 2 NAND gates, but you can make a clock with 3. How does that grab you?
It's pretty cool.
Yeah, that's cool. It's cool. Now, if you wanted to make a better clock, you probably would put in a crystal, symbolized in this way. And then you'd have the crystal resonate at the natural frequency of this circuit. And then you'd have a stable clock. The other clock would be, I would call it unstable as a function of temperature. So as temperature changed, the clock would drift. But if you put in a crystal in there, you'll get a fixed frequency. Crystals are interesting. They're typically shaped like tuning forks inside, made of little quartz crystals vibrating at a set frequency that's a function of their material properties and their size. And you can buy these in different frequencies. And in fact, you typically have one for most of your CPUs. So if you see an Arduino, there'll be like a little metal can. Inside of that can is a little crystal. That'll give you a nice stable clock. And it'll be as accurate as the watch on your wrist. In other words, those are typically run as quartz movements. So that's that. That was question 9. So the answer is true. Using just 3 NAND gates, you can build an oscillator. And it's true because the NAND gates act like inverters, and 3 inverters can make a ring oscillator. Let's take a look at any other questions about this. It's kind of interesting because we've got the first example of feedback now, and you haven't seen one yet. So that's cool. That's cool. Let's do 19 and 20 next. So I'm going to go up to 19. Let's see what we got. Okily dokily. Somebody writes, what is A plus A prime B in parentheses equal? That's a good one. How can we know? What could it be? Well, one thing you could do is you could make a truth table. Now, it's going to be true if A is true, so it'll be true in here. But what if A is equal to 0 and B is equal to 1? It should also be true. What if A is equal to 0 and B is equal to 0? Well, then it's going to be 0. So now it looks like F must be equal to either A or B. Or you could say F prime, which is where F is 0, is equal to A prime and B prime. But if that's true, then F must be equal to A prime, B prime inverted. So I inverted both sides. And that means that F must be equal to A or B, which is also true because of De Morgan's theorem. So either way you approach it, you could just say, well, this is what makes it false. That's the easy thing. Let's state what makes it false. And then use De Morgan's theorem on both sides of the equation. Well, invert both sides of the equation, use De Morgan's theorem, and you get a result, which is correct. What do you think of that?
Can you explain the truth table one more time, please?
Sure. So the truth table says, let's look at all possible inputs for A and B. So I count in binary, right? I'll number the truth table 0, 1, 2, and 3. So I'm numbering now in radix equal to 10, but initially I numbered in binary, radix equal 2. Typically, you number your truth tables in decimal on the side just to keep things straight. And then you look at your function f, and you say, what is going to make f true? Well, if A is a 1, then f will be true. Also, if A is 0 and B is a 1, then f will be true. But otherwise, f is equal to 0. And so then I say, well, if f equals 0, then f prime will be true if A is 0 and B is 0. So then I say, well, if that's true for f prime, I should be able to solve for f by inverting both sides, and then employing De Morgan's theorem. What do you think of that?
That makes sense. Thank you.
Sure. So now let's erase this and start from fresh. We'll do
Oh, wait,
problem
Professor,
20.
I'm sorry. I just had a quick question about that. Sorry about that.
Oops. Can I go
I
back?
wrote down the truth table, but the only question I had about the truth table was how come in rows 2 and 3 you're having a 1 in for F? Because wouldn't it be 0, 0 when you invert A?
So here, what's going to make f true? Somebody said f was equal to A plus A prime B. Right, that was the given. That means F is going to be true if A is true. So everywhere here, A is equal to 1, and therefore F must be true. So this corresponds to A. Now the question is, what corresponds to A prime B? Well, if A is equal to 0 and B is equal to 1, then A prime must be equal to 1 and A prime B must be equal to 1. So it's true when F is true when A is 0 and B is 1. And that's what leads me to put a 1 in row 1. And there's a 0 here because there's nothing that will make F true when A is 0 and B is 0. Because if A is 0, this part of the equation will be 0. When B is 0, this part of the equation will be 0 because anything times 0 is 0. What do you think of that?
Yeah, my bad. I was actually completely forgot about the A all by itself.
Yeah, that's important. That's important. Let's go on to the next. Oh, I guess I'll just start from scratch. 20. So this is 20, problem 20, homework number 2. Somebody said, what is A or B or C going to be equal to? Well, does it matter what order in which we do the addition? It's equal to A or B or C. It's equal to A or B or C with A or B first. So in principle, it doesn't matter in which order you do these things. So this is a correct answer because that's one of the elements. You couldn't get, for example, B or CA. That was one of the choices, and nor could you get A prime or B prime or C prime because that was another choice. That just doesn't work. But there is a choice that does work, and it looks like this. What do you think of that? In other words, the order in which you do your addition is not particularly relevant. You could have written A plus C plus B and still gotten the same answer. And you could even group it with parentheses to make sure it's evaluated first. What do you think? Is it clear?
Yes, thank you.
Good, good. Other questions about homework
Professor,
2?
can
Yes.
we do number 2? I was struggling with that one.
Sure, sure. Number 2. Let's have a look. What's number 2? Okay, well, I'll tell you. This is a 16-row truth table. And my little iPad isn't big enough for me to write out a 16-row truth table. So he asks, the problem is, what is the output for a 4-input AND gate? Well, tell you what, let's do a 2-input AND gate. Okay, it's true when all of the elements are 1. Let's do a 3-input AND gate. Oops. There. So now it's true when all the elements are 1, and otherwise it's 0. So now you should be able to do a 4-input AND gate. It's only true when all the elements are going to be, this is an AND gate, right? AND gate. Let me just, 3-input AND gate. So there's only one choice that shows a 3-input AND gate where all the inputs are equal to 1. And this is shown in the, well, I guess I'll call it 0, 1, 2, 3, 4, 5, 6, 7th row, numbering by r equals 10, radix 10. So that's that. What do you think? Does that sort of answer the question?
Yeah, I was thinking of OR gates.
OR gates.
So
Oh,
that
that's a
method.
whole other matter.
So it's actually pretty simple.
Yeah, this was an easy one. Oh, look at all the colors. Isn't that fun? So any other questions about homework 2? No questions? That's cool. That's cool. Let's take a look at some of the questions that you might see in homework number 3. Homework 3 has not been, I guess you might say, publicized yet. What's the difference between an axiom and a postulate? Anybody have any ideas about that? Axiom versus postulate. Any ideas?
None at all.
None at all. Well, the answer is it's a trick question. There's no difference. How's that? They're equal. And what is it? What is an axiom anyway, or a postulate for that matter? And the answer is it's something that's taken without controversy or question. In other words, x or 0 equals x. X or 1 equals 1. X ANDed with 1 equals 1. Well, equals x. Sorry, that's the identity. X ANDed with 0 is equal to 0, right? We don't prove these things. These things are given, and we take them as, well, artifacts of the basic assumption of the Boolean algebra. And if by some chance these artifacts should stop working, perhaps on a quantum computer somewhere, then we'd say, oh, everything we know is wrong because we built a mathematical system on top of these axioms. And if these axioms are not true, in other words, if A plus B equals B plus A, right? If somehow this ceased to work, then we would break the algebra. We'd have a non-functioning algebra. So this is an interesting idea, because what we started with was, we said there is a set of Boolean numbers. And in that set, we have 2 elements, 0 and 1. And all of the Boolean algebraic operations which we can perform on the set are closed on the set, which means everything will result in a 0 or a 1. Then along comes quantum logic, and you can have numbers that are not 0 and are not 1. And so this ends up becoming sort of a, I'll say, violation of the basic premise. violation of the axioms. So that's an axiom. There you go. Theorems are built on top of axioms. So let's assume for the moment that A, B prime is equal to A prime or B prime. That's a basic result. It's a theorem. And everybody now knows that is what they call De Morgan's theorem. And that's the answer to question 1. It's De Morgan's theorem. So now we've got an idea about axioms and postulates and theorems. Theorems are built on axioms, and theorems will break if the axioms break. Let's take a look at another one. How do we simplify A times A or B? I'll let you guys work on this a little bit. What can I do? You tell me.
Would it just be AA plus AB?
AA plus AB. That's true. But what is A times A?
Just A.
That's A. And can I factor A out from this expression?
Yep.
Why not? So A times 1 or B, right? Because I have a common term here, common term. And what's 1 or B?
1.
That's 1. So now I have A ANDed with 1, which must be equal to A. And that is the answer to question 2. And we get this idea that maybe the algebra is correct, but we can validate the idea. How would we validate this? How do I know this is true? I could do a proof, right? Other than by algebraic manipulation, I can do a proof by perfect enumeration. I can write A. I can write A or B. I can write A times A or B. And now I can see that this column is equal to that column. And therefore, A equals A times A or B. How's that grab you?
Pretty cool.
It's good. It's good, right? And if you say, I don't follow you, what you really mean is, I don't think what you're saying is rational. How's that grab you? Sorry, I'm just kidding you. So there, question 3. How much is A or 1?
That's just 1.
Yes, that's 1. And that's the answer to question 3. Oh, these are easy. Let's skip ahead a little bit and try and do something a little bit more complicated. Let's try question 5. A, B, or A prime C, or B, C. What's that equal? Hmm. Can I write a truth table for this? Let's call this F. And we'll have A, B, and C. And this will be true if A and B are equal to 1. Trying to keep things neat. It'll also be true if A is equal to 0 and C is equal to a 1. It's also true if B is equal to a 1 and C is equal to a 1. But notice when I said if B is equal to 1, if C is equal to 1, it meant here, here, and nowhere else. That's kind of interesting because those things were already checked. Those things are already there. Those ones were there from before, which means that BC didn't contribute anything. And therefore, F can be written in a simplified form, AB or A prime C. So by filling out the truth table, you can see which product term, and these are all product terms, you can see which product term contributed to the truth table. And if a product term does not contribute to the truth table, it's a redundant product term and can be removed. That will give you a more minimal form. And moreover, if you like, you could go through and do an algebraic manipulation that could, in principle, give you the same result. But it might take a while. So there's that. That's question 5.
So, Professor?
Yeah.
So the reason why we got rid of BC was because it just gave us answers that we already have, or?
Yep.
Okay.
It didn't help us to fill out the truth table with any additional ones. Therefore, BC must have been redundant.
Okay, thank you.
Let's see if we can go to another question here. Let's see. What's the difference between a postulate and a law? In other words, if we say, because it's the law, like it's associative law or it's commutative law, what do we have?
Would it be because a law is supported by a theorem?
Nope, that's close. It's just backwards. So theorems use laws, and laws are identical to postulates. In fact, you can have a thing called the associative law, and you could say that's a postulate. And you could have something called the commutative law, and you could say that's a postulate. And an example of the commutative law might be something like A plus B equals B plus A. That's commutation. And we have a commutative law in the regular algebra we learned when we were in middle school. Commutation works for that too. And we say it's a part of the algebra that we accept without question. Nobody seeks to prove it because it is it's a feature of the algebra. And if you were to say that that feature no longer works, well, then the algebra as you know it would be fundamentally changed. It would not be the same algebra. Here's another law, the law of the complement. Or maybe the complementary. So then A or A prime equals, what's that equal? I'm learning how to use my Blackboard. What does A or A prime equal? Well, if A is equal to 0, 0 or 1, what's that equal?
1.
1. If A is equal to 1, 1 or 0 must be equal to
1.
1. So that means that A or A prime must be equal to
1.
1. And that's the law of the complement. It's a basic postulate. So that's a good one. Here's one. A or B times A or C. How do we simplify this? This is from question 16. Well, I guess I can cross multiply, right? I get AA or AC or AB or BC. But the ability to cross multiply comes about because of the distributive law, right? So that's from the law of distribution. And we're used to that. And then using the law of distribution, I get a new formula that I can proceed to simplify. And then I can factor out A. And so I can get a simplified form, but the act of distributing A across the parentheses is the law of distribution. Anybody get confused by that?
Can you just repeat the last step you took when you had the A and then parentheses 1 plus C plus B?
Sure. So what I did was I took A and I factored it out of all the product terms where A appeared. So A times 1 is A times C is AC, A times B is AB. And then you have to say plus BC. And so that's where you go and you say, but 1 ORed with anything is 1, and A times 1 is A. What do you think of that? Does
And then
that
the
sort of work?
BC, so the BC was just left out before that.
Yeah, I
That's
left
where I was a little
it
confused
out.
with where they.
Yep. Sorry about that. A little blemish in my presentation there. So there's that was question 16. Pretty cool. Pretty cool. What's going on here? Plus. Oh, here we go. A times A or B. What does that equal? This is a good one, right? Because it's equal to, using the law of absorption, A times A or AB, which must be equal to A or AB, which must be equal to A times 1 or B, which must be equal to A. They call that the law of absorption.
Professor, do we have to know these laws by name for a test?
No, you can always look them up. You'll have, a question that'll say match with the right postulate. That's typical homework question. And you can look it up. Nothing wrong with that. Open book, open notes for the
Professor, is
homeworks and for the tests. Yes.
Is there any way we could backtrack to homework 2 and go over question 22? It deals with postulates as well.
I don't think we did 22 yet. So you want to do homework 2, number 22?
Yes, please.
Yeah, let's start a new one. Let's start a new page. And right now I'm on homework 3. So what I want to do is close out of homework 3. And then yeah, skipping around like this is less easy because I got to close one Blackboard assignment and open another, but it's not impossible. Let's take a look and see what we got. Question 22. All right. Question 22, match with the right postulate. Is it the law of identity, the complementary law, the associative law, or the commutative law? Commutativity says A or B equals B or A. So that doesn't sound right. Can't be the commutative law. Identity says A times 1 is equal to A. A or 0 is equal to A. So that's identity. So it's not that one. Any ideas?
Is it the associative?
That is the associative law, because associative, it's always involving parentheses, right? The law of the complementary doesn't involve parentheses necessarily. And so the only thing that really keeps these two things from being identical is the order in which you do the computation. And in our case, it doesn't seem to make much difference. So that's what I would say, associative. Any other questions about homework 2?
Can we do the next one also, 23?
23. Okay. You have created the whoa, what did he say? The maximum number of whiteboards? Really? That's stinky. So what do? I gotta delete them now? Clear all drawings. Now I can make new whiteboards? No, because they're still there. Well, maybe that's, okay. Learn to use Blackboard. I'll put that on my list of things to do. A plus B equals A. First of all, is this true? Let's see. A times A or AB, right? Because I use the associative law. And then I have A or AB. Didn't we do this already? Then I factor out A, and I get 1 or B. And that must be equal to A. I'm pretty sure we did this. So that's the law of absorption, right? I could get the book and show it to you, but I don't think my iPad will let me. That's actually a good question. Does the iPad let you do that? I don't know. So that's the law of absorption. Other questions for homework 2? All right, hearing none, I'm going to close this out and go to homework 3. Course content. And let me just take a look here. What are we doing? We got theorems and postulates. Edit the test. And going back and forth, it ain't easy. So let's see, where were we? Question 16. Oh no, he's giving me a hard time again. I don't know how to erase the blackboard. I think I'd like to erase all the blackboards. Maybe if I hit edit and then just poke at the minus signs. Just a minute. There. All right, let's try some more. We'll do question 19. A or A equals, what does A or A equal?
A.
Yeah, it's equal to A. And that, is that the, what is that an example of? You
Would
can
that be
always
like
get,
identity?
well, identity would be something like this. A times 1 is equal to A. Or A ORed with 0 is equal to A. So what you want to do, in case you're wondering, is you want to go and you want to check the list of theorems and axioms, which I think are somewhere in, yeah, page 51. So go to page 51 of the book. and look it up. And here's one that says x or x equals x. And that is theorem number 3. And that theorem is called the idempotent theorem. So you can look, open the book, look it up. What is the dual of the idempotent theorem? How do you find the dual?
Is it x and x equals x?
There you go. That's the dual. So idempotency. That's kind of cool, actually. I'm Googling it because I'm interested. Item, I figured it was Latin. Item comes from the Latin and it means the same. So potent is just regular English, because when something's potent, it means it works. So it works the same, idempotent. How about that? It's idempotent. That's how you remember it. You get it from the Latin. Item. It's an item, means it's the same. Huh. Well, it's an item. Item. I didn't know that. Item is from the Latin. And here you can see it's the same. That's pretty cool. So that's how you remember that. How about that? See, now I learned something because I didn't know about the Latin thing. That's cool. It's cool. You have Google here. Boy, what would we do without Google? I don't know. How about this? Canonical. That's a good word. I like that word. We could get that easily because it comes from the canons of the church, right? Which means it's like the law. But what is a canonical etymology? I like the etymology thing because it kind of, oh boy, it comes from the Latin again. According to rule. Oh boy, we're all learning Latin today. Isn't this fun? Boy, learning is fun, Professor Lyon. Yes, it is. Very fun. According to rule is the way canon is translated from the Latin. Canonicus. Canonicus, according to rule. So the canon law, the canonicus law, is according to the rule, canons of the church. Canonical is a form which is used in Boolean algebra. Now, where does the term Boolean come from? Give you a hint, it's an eponym. Boy, this is good, right? Who knows what an eponym is? Nobody? Really? It's a word named after a person. So Einsteinian notation is an eponym for Einstein and his notation. Boolean algebra is an eponym for George Boole and the algebra that George Boole worked on. So George Boole was a person who lived during the Victorian era, and he worked on Boolean algebra. And that means Boolean is actually an eponym. That is a word named after a person. Boy, we're learning a lot today, aren't we? Isn't this wonderful? Learning. Oh, learning's fun. Okay, so here comes a canonical form. If F is equal to A or B, how can I form the canonical version of what is a sum of products? So this is a product, that's a product, and this is a sum. And the answer is the canonical sum of products, which I'm going to abbreviate as CSOP, is equal to A times B or B inverse, which we know is also going to be a form of 1, plus A or A inverse, also a form of 1, times B. We then use the associative law and write AB or AB prime or AB or A prime B. We then notice that AB is written twice, and therefore we can write our new canonical sum of products as AB prime or AB or A prime B. And that is a canonical sum of products. And the reason why it's considered a proper form is every single literal appears in every single product term. So all product terms oops. I wanted to get rid of, oh well. All product terms in have every literal. There's a window in the way on my blackboard, which you don't see. And it's sort of annoying because I can't get rid of it. So that's a canonical sum of products. Canonical sum of products. Let's do another example. C or D or AB equals F. How can I find the canonical sum of products? Well, this one takes a little while longer. But one thing I could do is I could write out A, B, C, and D. Whoops. There. Yeah, it's so hard to do this on the iPad. And now, what will make F true? And the answer is wherever C is equal to a 1, if C is equal to a 1, F will be 1. If D is equal to a 1, F will be 1. If A and B are both equal to 1, it's a 1. And otherwise, it's a 0. Now I can find f prime. F prime is going to be here, here, and here, just 3 places. A, B, C, D, all 0, or A, B, C, D with a prime on everything except for B, or A, B, C, D with a prime on B, C, and D, and that's it. And if that's f prime, then f must be that I could say inverted, and I could certainly invert it, but then I would have instead of a sum of products, I'd have a canonical product of sums, which is cool. A or B or C or D times A or B or C or D, B prime. I'll just put a dot in there, times A or B or C or D with the A prime. And that is a canonical product of sums. And the canonical product of sums is interesting because it has every single literal in each one of the product terms. Well, each one of the sum terms. So this is a sum term, and they're all being multiplied together, and that's why we call it a product of sums. So what that does is it says canonical forms have canonical sum of products or canonical product of sums. Those are the only 2 kinds of canonical forms that we know. And so that's interesting because they have every single literal in them. And in fact, you'll find 2-level logic canonical forms in section 2.2.2 on page 56. How's that grab you? Canonical forms. Turns out if you wanted to write out the product terms, you'd have to write out 13 different product terms in the canonical sum of products. Every time there's a 1, you'd have to write out the 4 product terms. In this case, it would be A prime, B prime, C prime, D. Anywhere there's a 0, you'd use a prime. Here it would be A prime, B prime, C, D prime. Here it would be A prime, B prime, C, D. And here it would be A prime, B, C prime, D. And then it goes on and on. It's a little tedious to do it for the large functions. But we can do one that has, has a fewer number. Let's try this, ABC. F. Zero, 1, 2, 3, 4, 5, 6, 7. So now, given the following truth table, write F in canonical sum of products. This will be M0, M1, M2, M3, M4, and M5. Whoops. 0, 1, 2, 3, 4, sorry. M5, M6, M7. There we go. So anywhere there's a 1, the so-called min term, M sub I, must be available. So F must be equal to M0 plus M1 plus M4 plus M6. And I can write this in canonical sum of products shorthand notation: 0, 1, 4, and 6. Moreover, I can write it out algebraically, and I write out A, B, C, all inverted, or A, B, C with only the first two variables inverted, A, B, C, last two variables inverted, or A, B, C, and only the last variable inverted. This corresponds to 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 0. So little blemish in my presentation there. That should be a 1. And you can see where those rows map directly into these numbers. I also change colors for no particular reason other than we can. And so that gives you an idea as to how you can get the canonical sum of products directly from inspection of the truth table. Canonical. It's canonical from the church. So when you're reading chapter 2, you'll be getting into what's called the min terms. These are min terms. Min terms are nothing more than product terms. And those product terms have a direct correspondence to the row that you're in the truth table. So that's kind of cool, actually. That gives you an algebraic, I'll say, analog to the truth table. Every element in the truth table that is a member of the onset has a min term associated with it. Min terms. It's cool. Min terms. Questions about min terms? Let's see how it relates to logic. A and B is a product term. A and B ORed with A prime and B, that is a sum. And these are product terms. And hence, this is what you call a sum of products. I really have trouble with this iPad. Do people like the iPad or do they prefer the camera?
I like the iPad much better.
iPad's better? All right, we'll
Yeah, the
stick to
iPad
that
is
for.
good.
Okay, let's stick to it for a little bit. It's just so constraining, but I'll just try and neaten up my writing a little bit. And then let's think about this a minute. Plus is a disjunctive. And times is a conjunctive. Now, now it's etymology time again. Disjunction comes from the Latin disjun. I'm having trouble with this one. Yeah, you guys will help me. I just want to say this. DISIUNCTIONEM. What? Is that, yeah. This is the trouble with Latin. They got a different word for everything. Disiunctionem, I guess. Disuncium means separation. It comes from the stem disungere, from dis, joined together. I don't know. Disjunction. Well, that's not very educational. I can't pronounce it. I wonder if, does anybody here know Latin well enough to pronounce this? Or at least attempt to pronounce it? No? Nobody? Nobody takes Latin anymore, including me. Well, that's too bad. Maybe we'll stop with the etymology thing. It comes from the 1400s. Disjunctivus. Think disjunctivus. 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 Well, okay, I get it. It's a different language. Gotta learn it, I guess, or not. Anyway, they call it a disjunctive form. And so when you're looking at the test, question 21 asks, is a canonical product of sums a disjunctive form? And the answer is yes, it is. Canonical sum of products is a disjunctive form. A disjunctive form. So that's an interesting point. And the canonical product of sums is a conjunctive form because it's using times. Canonical product of sums is a conjunctive form. How about that? And if you take philosophy, they'll be using things like conjunctive like this and disjunctive like that. So it's the same meaning, just different symbols. Let's try another question. So this will be question, do we have time? Oh, we're almost out of time. So with 20 seconds to go, are there any questions? Well, I guess we'll try and use the iPad a little bit more frequently now. I thank you all for your time, and I hope you enjoy the rest of the day. It looks like a beautiful, clear day, if not a little bit cold and windy.
Thank you, Professor.
Thank you.
Thank you, Professor.
Thank
Thank
you.
Thank you.
Thank you.
Professor,
Yes.
I was just wondering for tests, I know it's open everything, but is it going to be like is it going to be like a class period or is it going to be like a day?
It's going to be like 2 weeks.
Oh, okay. Awesome.
Yeah, you get 2 weeks, and you can look at the test without starting it. You can print it out. You can look at it offline. Take your time with it. It'll be like 100 questions. And then basically you can log in and put in your answers whenever you feel ready. And then you'll get feedback right away. And then you get to try again and you get the higher of the 2 grades.
Okay, thank you.
Sure. Thank you.